Hey, welcome to another coding session. Continuing with Bangalang, the language we're creating. I'm going to give a little bit of a recap. I haven't done that in a little while. I think it'll be helpful. So we're creating a language called Bangalang. I just called it that because I thought it sounded funny. But the idea is that it's a low-level, quite explicit procedural language. It's going to have manual memory management. At the moment, there's not a whole lot of memory management to do, but that's the idea. So yeah, quite low level. And the kind of end goal is that I would like it to be really easy to take some code in the language and execute it on the CPU or the GPU, wherever you like. It should be quite a seamless, easy experience to move between the two. Obviously, that needs to be kind of parallel-oriented code because that's what the GPU does. If you try to do some serial code on the GPU, it's probably not the best idea. Yeah, so we have, quite a few features in the language already. We have like procedures. We have if-else. We have for loops. This is like a while loop. We still use the keyword for. That's something we borrowed from Odin, which is the language we're using to write our language in, or write our compiler in. We have pointers. Here's a pointer. We have arrays, pointers to arrays. And you can see this is a pointer to an array, but we just go like this. So there's auto dereferencing. We can just index directly on a pointer. I think that's more or less what we have so far. Well, actually, the most recent features we added was we can call C. So this is glfw is a C library that we're calling. And we also just added floats. I'm going to take this out because that was kind of some testing. So now I feel like we have all the ingredients that we can do some OpenGL rendering, which I'm pretty excited about. I feel like this is the first time we actually do something kind of interesting with the language. Like right now, we can open a window. That's what glfw does. But actually rendering something, even though it's just going to be a triangle for now, I think that's kind of cool. And the main thing really we're going to need to implement, I think, for this, because we're going to need to do lots of different OpenGL calls, is we want this kind of definition of extern procedures, which is to say C procedures. We want to be able to define this in the language. Like at the moment, if I go to type checking, yeah, we can see that they're defined here. They're like hard-coded. So I want to take that out and instead define them here. And at the same time, I kind of want to change the syntax a little bit of procedures. I want it to be just like this. So, it's the same as this. It's like name : type. We hear the type is an external procedure that returns a cend. And then, so we have a few procedures in here. So this would be the same. We put an equals. So we say equals, and then we put the procedure body. So this would be equals like that. And kind of the reason that I want to have this kind of syntax is because it's really aligned with like this. This is just declaring an I64. So it's like the name : type equals value. So here we have name : this is the type, procedure returning an I8 equals the value, which is the body of the procedure, which could either be a scope or just a single statement. And another thing is I want to remove this need for a return type. At the moment, the grammar requires you to have a return type, which is why we were returning true from the assertion when we don't need to return anything. So I think the first thing we need to do is update our grammar to handle those changes. So it's mostly this procedure here that we're changing. So the equals, we're moving to the end just before the statement being the body of the procedure. And I'm going to put that in brackets because that's optional. For an extern procedure like this, we don't need the equals something. So it's optional. And then we're also making the return type optional, so that's this this here, right? Yeah, the arrow type, that's the return type, so we make that optional. And then over here before the proc, we could optionally have the extern directive. So name of the procedure, colon, optionally it's extern, proc keyword, which maybe at some point we'll remove. I'm not sure that it's really needed. This is our parameters to the procedure, so that's not changing. But now our return type is optional, and the procedure body is also optional. So those are the changes to our grammar. In terms of tokenization, I think the only change is we need to be able to create a directive token for that hash extern. We can't do that yet. So let's copy this. We don't need all this stuff. This is kind of determining what type of token it is. So we're creating a directive token, which needs to start with a hash. And then after that, I think I'm going to just keep all this. So it could have any of the characters that are valid in an identifier after that. So we just need to add this directive token type, and then everything should be happy. So a directive is a hash followed by an identifier, kind of. All right. So now this should tokenize properly. Hey, while we're at it, let's make it look pretty. Got some data types that we can add to here. This is the syntax highlighting in CLion, which is the IDE I'm using. There we go. Now our CNs are pink and our externs are yellow. Very nice. So parsing is going to change. When we parse a procedure, the equals we have moved down to here before the statement. So this is the body of the procedure. And we also want to do like an if peak token type of thing. Because it's optional, right? So if we find an equals, then we're doing the procedure body thing. If we don't find an equals, we're not. And we also made the return type optional. So at this point, if we find an arrow, then we do arrow and we pass the type. Otherwise, there's nothing to do if there's no return type. And I'm going to steal this code and bring it up here, because between the colon and the proc, we also have another optional thing, which is the directive. And what that's going to do is set the directive of the procedure node. I think that's it for parsing. I think that should parse our procedure correctly now. Type checking. Okay, so this is already some procedure stuff. This is where we take the procedures, any procedures we find in the program, and we create these procedure objects from them. I actually kind of want to change this at some point, but anyway, let's do this. One thing we need to do is make sure we pass the directive on to this procedure. And then here we're basically saying the first node is the name. This is the children of the procedure. The first child node is the name, which is still correct. But here we're saying everything else except for the last node is a parameter. But now we're saying The reason we say that is because the last node was always the statement before, but that's not always the case now. So I think we need to change this condition, and the condition I have in mind is simply that the type needs to be identifier, because all the parameter nodes are going to be an identifier node, and then the statement node is going to be something else, like declaration or assignment or whatever it is, scope. So by checking this, we should make sure that these are the parameter nodes. I think that's everything we need to do here. Type check procedure has that same kind of thing. So I think we still need to check that it is, that we're not going past the end of the children. But we want to do the same check, I think. That the identifier is correct. Yeah, that it's an identifier. That's how we know it's a parameter node. And now this type checking of the statement is optional because there might not be one. Again, this is the procedure body that we're type checking now. So I just want to make sure that we do have another node to check. And if we don't, then we don't. We skip it. But actually, I think it's probably good to add some more checks here. So depending on, if we're talking about an extern procedure, then it should not have a body. Like this should not exist. So this is saying that it does exist. So if we have an external procedure and the statement, the body does exist, then I think I want to throw an error. Where's an example of some error? There we go. Failed to type check procedure. And let's say external procedure cannot have a procedure body. So I guess that's the name node. And I'll just put node for these, that's fine. And then I want to have another one which is kind of like, okay, but if it's not an extern, then we want to make sure that there is another child here. And if there isn't, which this condition says, then let's say procedure must have a procedure body. Now it's kind of the opposite. So extern ones should not have one. Non-extern, or just regular procedures, should have one. I think that's a nice thing to do. We might get rid of this at some point because we might be able to just like define a variable which has a type of procedure but hasn't been assigned a body yet. That could be a thing in the future, but not yet. So I think that's type checking of a procedure. Generation, I guess, will also change. So we hard coded this before. Let's get rid of that. And instead, I think what we want to do is just go, again, if we're talking about an external procedure, then we just want to output extern in the name and then return. That's all we need to do. So that's instead of hard coding it up here, we actually, when we're generating the procedure, we output the extern thing. I think that's it. What happens if I run that? Failed to parse statement because it found proc. Yeah, if it's a procedure, we should be doing this, not this. And I think it's because of this code, which I've put a note on because I don't like it. It's trying to identify whether it's a procedure or not by looking at the combination of tokens. and it said identifier colon equals proc, but we moved the equals now. So I think instead what we want to do is we want to say that the next token is either proc or extern. Still, I feel like this is not nice code. It's quite brittle and it's probably going to break again at some point. But it should do it properly now. Okay. So we get our window. So now we are using these definitions actually. We're defining here and calling here. Very nice. So I've got a list here already that I created. These are all the procedures we're going to need. I thought it was going to be a bit tedious to try and create these. Hopefully they're all correct enough. But I just thought it was going to be tedious and time consuming to do it during the session, so I pre-did it. So we have a few more GLFW procedures, some OpenGL constants and a whole bunch of OpenGL procedures, and a GL utility procedure also for error handling. And I have this other project, which was kind of like a fluid simulator, but it doesn't really work very well, but it has very similar code. So I think we can just like copy the code here. We need to actually get the window from this procedure now. So I think this just kind of makes the OpenGL context of this window, it makes it the current context so that when we do OpenGL calls, it will be linked to this window. I think that's what it does. I'm not sure exactly, but I think we need to call it. And here's our main loop. We're just going to take a little bit from this. So we don't need the stopwatch stuff. And let's just put a to-do render here. Take out the dots. And yeah, so I guess this poll events is now linked to this window because I don't know why this doesn't take a window. Or maybe it just does it for all windows at once. Anyway, this needs to be in brackets, and we don't have the not operator in our language yet. So I think we need to do like equals 0 because this returns an int. So equals 0 means that it's false, like it should not close. And I think this is never going to evaluate to true, but I don't know, it's kind of nice to have the loop like this anyway. Okay, unsupported register size. We have an issue already. Let's check what that issue is. Generating a call. So it's the extern procedure, and we're getting the return type. Well, this is the register of the return value. And it doesn't have a data type. So probably, do we have a name node here? Name node. So this is that GLFW make context current procedure, which does not have a return type. That's a new thing for us. So I think we need to handle that case. And while I'm here, actually, we have some issues here. We have some issues here with the way that we do this. This is our alignment, a procedure alignment. Because when we call a C procedure, we need to make sure that the stack is aligned, 16-byte aligned. And this method of doing it is not great. It has a lot of flaws. So while we're here, I think this is like the biggest issue we have right now, and we need to clean this up. Yeah. So first, let's move our return values. So let's fix up the return value. So we'll just move this out. That's for the non-next turn, and this is the return value for the X turn. And then before we get to there, I'm just going to say so the data type of the procedure node is the return data type. And so if it doesn't have one, let's just return an empty object. And that should avoid issues with this. This equals equals. Okay, I think we're going to need to go to the drawing board here. Okay, so here we have a stack. Let's go over here and start something new. So let's call this the call E stack. What I'm going to do here is try and model like what does it look like from the perspective of the call E and the call when we call a procedure. So like right here, this code we're looking at is the generation of the call. So that's like the generation of, say, this line where it calls the procedure. And then we also have the generation of the procedure itself, which is where we provide the body of the procedure. Or for an extern procedure, all we do is like extern. We can't see it now because it failed generation. So those are the two areas we kind of need to see like what's going on. So let's say, you know, as the callee, we've just done some random stuff. We put some variables on the stack. Now it comes time to call a procedure. So here we're talking about calling a Bangalang procedure. So not an extern procedure, but a Bangalang procedure. And in that case, the calling convention is that we put some parameters on the stack. Actually, we put the return value on first, and then some parameters, and then we call, right? Then we call. So then control goes over to the procedure stack. So this is the stack from the point of view of the procedure. And it does not know about these. But it's going to have this return and these parameters. And then it's kind of like this here is from the point of view of the procedure, I want this to be stack 0. So this is kind of like the start of the stack frame, I guess is the terminology for the procedure, is here. So this stuff here is in the stack. It's been put in the stack by the callee. So the positions of these are going to be negative relative to the stack frame. Bear with me. That's kind of the concept I'm going to go with. So here we're going to have the instruction pointer. Because when you do a call, implicitly that's what the assembler is going to do. It's going to put the instruction pointer here on the stack. But that's within the stack frame of the procedure. And then again, you know, we can put a bunch of variables on top. So that's kind of how it looks. Now, the issue with this alignment stuff is that I'm only doing the alignment when it comes to an extern procedure. I'm saying, okay, before we do the call, let's make sure the stack is aligned. But what if we do the call from within another procedure? Part of the problem here is that we're not really accounting for this. Like we should go stack size plus equals something, because we're effectively allocating some space into the stack, but we don't know what this is. You know, this it's a really weird statement, but basically what it's saying is like, say the stack, say RSP equaled 20, but it needs to be aligned to 16. We want it to be 32. So the misalignment is like 4. Like it needs to be a multiple of 16, but it's 4 past, it's at 20. So then what we need to do is we need to allocate 12 onto the stack. And that's what this needs to do. And then the amount that we allocate, we also need to say, okay, we've allocated that space. Please be aware of that. Otherwise, that's going to cause issues later on. But we also need, when it comes to our own procedures, we also need to align these because the way, or do we need to align them? That's actually a good question. Well, because we're resetting, because the way I want to do it is I'm basically resetting the stack to 0. When we do these calculations with the stack size, for this to work, for the multiple of 16 to work, we need to make sure that this stack 0 is also a multiple of 16, effectively. And we want to make sure that these here, maybe I'll move this down so it's still all aligned nicely. These here, they still need to be snugly up against here so that when we calculate these positions, it's nice. So this is where we need our alignment padding. Our 16-byte alignment padding. We need to put it in here, the right amount of space, so that after we allocate these, this point here is a multiple of 16. So then when we say like, okay, the stack is starting from 0 for this procedure, blah, 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 and then up here we call an external procedure which requires alignment, we can just do align, and then we do the call, the external call straight after that. And because we know this procedure started on a multiple of 16, we can perform this alignment. I hope that makes sense. It's like kind of complicated and confusing, but it's super important to get this right. Otherwise, it's just going to be a mess. So actually, I think I'm going to move this out so that here we're just sort of like handling the parameters for this. Here we're handling the return and parameters for this. And then in both cases, we want to call the procedure. Okay, but this actually needs to be different, doesn't it? Because I guess for an external, we do want it to happen here. But like we said, for our own procedures, see, we're allocating for the return, we're allocating for the parameters, which is these guys here. We want to do the alignment first. So we actually need to do it up here. We kind of need to like count up the size of all these things, then figure out how much padding we need to do and put the padding up here, which is confusing. Maybe first we'll do the easy case, which is extern. So we know the stack is aligned properly. So if this is not aligned, then we can say or maybe we can just say misalignment is this. That's how far off we are. Is that spelled right? I think so. So, and if we are off, then we need to do a sub. Print if line, and this is to 16-byte align the stack. But it's actually 16 minus the misalignment. Because this is saying how far past a 16 are we? But we want to actually say like how far is it to the next 16 barrier, which is why we need to go 16 minus in both of these places. So that should perform the correct alignment. I guess this call stack size is kind of what we want to pre-calculate. So maybe I'll take all this. Ooh, what did I do? I don't know what I did there. Hopefully nothing too bad. So maybe I'll take this up here, and instead of doing this allocation, if we're deallocating the return, then we add the return byte size to it. And then for all the parameter nodes, but we can't, I think it's a bad idea to do this increment because it's going to mess with this. So it's kind of like param index equals child index, or param index is less than that, and param index plus equals 1. And then we just do param index. And then we're just going to say, hey, get us the byte size. Like so. So that should give us the size of our return plus the size. What happens if this is an empty data type? Then it's probably going to throw an error. So we first probably need to check that there is a return type. So that should give us the size of the return value and the parameters. It should give us the size of all this. So then we should need to, then we can figure out how big to make this so that all of this together will result in this point being a multiple of 16. So that'll be something like this. So it's like stack size plus the call stack size. That tells us our misalignment. And then I think I'm going to do call stack size also gets increased by that. If we don't deallocate the return, I think we still need to account for this. This is complicated stuff here. More complicated than I like. I don't like complicated code. Usually I find there's like just about always a simple way to do things, but this is unfortunately complicated. So this is where we actually allocate. like so. And then we do the expressions. And then at the end, we deallocate that amount. But that should be after the procedure call that we deallocate. So maybe I'll bring this out here. And maybe we should do that here as well, because we want to make sure we've allocated some stuff to a line, but then that's like wasted space afterwards. So we want to make sure we deallocate it after the call. Okay, so we're allocating everything. We're deallocating everything. We do have, I feel like, this issue of we might be deallocating the return when we shouldn't. So I think we always need to account for it in the size. And then when we're deallocating, if we're not supposed to deallocate the return type, then we should not deallocate this amount. But also, if we're not deallocating the return type, which is required in some cases if it's embedded in an expression, we need to make sure we keep this and this. Because if we keep just this and remove this, then it's going to be the wrong. Our stack size is going to be wrong, or we're going to be pointing to the wrong place. So I think what we need to do is after we've done all this, and the only other place we use call stack size is deallocation, I think we need to say if we're not deallocating the return, then we need to reduce this call stack size so that when this deallocation happens, it ignores the return. So that's the byte size of the return and the misalignment, this guy here. So yeah, that should mean that when we come to this deallocation, these two things stay in place, and it's just these that get removed. And when this context eventually gets cleaned up, it will then clean these up, which should happen at the end of the expression. So it should still get cleaned up, but we don't want it to happen straight away. Okay, that was super complicated. I really hope that it's right. I would not be surprised if it's wrong. Now when we generate a procedure, we've also got some changes to happen here. Because at the moment we're taking the existing stack size instead of resetting it, which means that it could be anything. Because the way we parse the program is like we check all the statements, like this can happen, this can happen, all these statements happen, and then whatever the stack size after that is, that's what the stack size is when it starts processing or generating the procedure bodies, which doesn't actually make sense. That like these statements should not dictate what the stack size is when you enter a procedure. So yeah, I'm really not sure if this stuff is making sense. I hope it is. But what we need to do is when we copy our context, I think the stack size thing needs to only happen if we're inline. And the only case where we're not inline is basically when we enter a procedure. So by putting this in here, we're basically saying that when we enter a procedure, the stack size is reset. And then when we exit the procedure, when we exit the procedure, we don't want to take into account the parent stack size when we figure out how much to deallocate. It's just this. So if it's inline, we do that. If not, in the case of a procedure, it's just the stack size. That's what we need to deallocate. Okay. Okay, now that we've got that sorted, we don't actually, if the parameters, the return and the parameters should not actually affect the stack size, because they're down here below the start of the stack. So we take these out. And instead, what we need to do, I think, is we need to say, like, the offset is 0. And so we set that to the offset, and then the offset we need to reduce by the byte size of the parameter. So the first parameter is going to go to position 0, and then the second parameter will be negative by an offset of the size of the first parameter, and then so that everything will shift further back. Which means, I've just noticed this is the wrong condition again. No, this is the right condition, but we need to change it because we need to go backwards through the children now. Because the last child is, or the last parameter is the one that goes here. And we need to go back, back, back. So that's saying all but the last child. So how do we do this? We want to go from, let's call it param index again, is the length of the children -2. That should be, like, because the length -1 is the last node, but the last node is the statement. So then we come back 1, and this should be the last parameter. And while parameter index is greater than 0, is that right? Greater than 0? Yeah, well, actually we want the child index. So I guess it's going down to, oh no, but the first child is the name. So I think that's right. Really not sure. But I think we're not going to have this child index business here. So this is going to go from the second to last node to the second node. I think that's right. And each time it's going to, we're going to move further into the negative. And then after that, we do the return. It goes to the offset. I think that's right. I sure hope that's right. And then the statement node is the last node. And I think now we don't need this. I'm going to go out on a limb and say we don't need this. But this, I think, is not right anymore. I think we just need to adjust for that. So this stack size is going to include the instruction pointer, that's this guy here, plus anything else we allocate. But the instruction pointer gets deallocated by the assembler. We don't need to do that. So we need to account for it when we're positioning our variables. But then at the end, we need to remove it from what we deallocate. We don't want to, we don't manually deallocate it. It gets done for us. So that's why we would remove it from there. So complicated. So complicated. Okay. Hopefully that works. Okay, well, we've got a window. Let's see, when the program gets more complicated. Okay, we're 45 minutes in. I feel like we've done a lot of the heavy lifting, and now it should be, fingers crossed, not too complicated to implement this OpenGL stuff. So let's start with, first thing we need to do is compile some shaders. So let's steal that code. Change it to, no, we do need proc, don't we? Change it to our syntax. We only have I32s. I think we'll put that here first. We can't do file handling. So I'm just going to say the source is a C string. Yeah, see, we need a C string of the source, and we also need the length. So source length is I32, and then we take pointers to those. We don't read a file. Boom, boom. So here we need GL compile status. That is a pointer. That is a pointer like that. A null pointer, size of info log. So this is one of those ones, I can't remember if I mentioned this before, but they have these hacky types where it's expecting a pointer to 1,000,000 I8s, so 1,000,000 bytes. So I'm just going to make this 1,000,000 bytes and then pass in a pointer to it, which means that the size is 1,000,000. Here we can do this in our language. We do have to put brackets though. This we're going to need to change, and we need an assertion. We don't have a concept of libraries yet, so we just have to put everything, or even importing, so we just have to put everything in the same file. So we'll put our assertion here. This, my idea, was to make this print B. I think this is the right order. Let's see. So my idea with this print B is, currently in generation, we have this hard-coded print procedure, and I just want to make another label so print B does the same thing. Print is expecting a string, which is a length and, no, this is the length and a pointer to the data. So the pointer is like kind of the first parameter, and this is the second parameter. I want to say, is that how I did it? Yes. So then we just need to add some type checking so that that is a valid procedure. And it takes different parameters. So the first one is the pointer. I guess it's a pointer to 1,000,000 bytes, our hacky type. So it's an I8 pointer to 1,000,000 bytes. And this is our length, so that's an I64. Yeah, just an I64. Let's see. I think that's it. I think that should be compile shader. Does that actually compile? That's just source and GL compile status. Right, I think we need to have it the same reason that null pointer is not working. We need to have it in here. Because currently in our language, there's no way of, like, if it's defined out here, we can't see it within the procedure. It just doesn't work. So we need the proper compile status, which I think we can steal from over here. Here's the hex, but we do not support hex in our language yet. So what's the decimal of that? And let's use the decimal, like so. Line 65, incompatible types. The length is a pointer to an I32, so I need to make that an I32 pointer. Okay, now we get undefined reference to a bunch of procedures. So we're going to do a hacky thing again. Last time we did hackily just put the linking to GLFW in there. Now we're going to put OpenGL also. Okay. That ran, but we didn't actually call this procedure. So let's try calling it. Vertex shader name. Vertex shader source is going to be a C string that we pass in. And then the length, I'm just going to measure the length of it and hard code it there. So a vertex shader. Here's a vertex shader. We're going to do like the most simple vertex shader possible. I'll explain this once I've got it kind of figured out, but here we go. Vec for position. Oh, no. Okay. And this needs to have a new line in it, which we don't support yet. Because I don't think we can actually, like, I thought this might work, but I don't think it does. 47 valid token. Oh, probably because of this, actually. So this is 86 characters. I don't think this is going to work, but let's see. Because I never made it, I never said that strings couldn't just have a new line character in them. Wrong number of parameters at 47, expected 3. Ah, yeah, because we need to pass in that it's a vertex shader. We need to pass in the type. Unterminated string. Yeah, so this doesn't work because we in the assembly you can't do that. Okay. So maybe we should not allow new lines in our strings. So I think we're going to have to do this, and we're going to have to add support for that because our language doesn't support having new line characters like that. We're just going to hack it in for now. So let's say final string is replace all new lines with, we're going to have something like this. So it's double quote, comma, 10, comma, double quote. I'll explain in a minute why that works, or hopefully works. Oh, I think we need, because I think there's an OK flag that gets returned. Let's just assume it's OK. Okay, so that worked, seems like. And what we did was we have like, so now we have this string, and then we have comma 10, and then another string, which is kind of similar to how we null terminated like this. Because we're defining bytes, we can define them as a string, or we can just say this is the byte 10. And the byte 10 means new line. I just happened to know that. So now these support new lines. And we didn't get any errors, so fingers crossed the compilation of that shader actually worked. I'm going to do the fragment shader now, and then I will explain like what the hell is going on with these things. I'm not going to like go into super detail about OpenGL, because this is not really an OpenGL tutorial, but I'll try to explain like generally what's going on. So this should be an out vec4 color, and color is just like that. So if I run that, still no errors, that's good. So what's going on here? In OpenGL, you pass in some positions of vertices. That's the simplest thing you can do. So in our case, we're going to pass in 3 vertices. We haven't done it yet. 3 positions, which are x, y, and z for each vertex of the triangle. And this vertex shader that we just created here is a bit of code that runs on the GPU for every vertex that you pass in. So this is the position that we're passing in. It's a vec3, which means it's an array of 3 floats, basically. This directive here just means we're using OpenGL 4.6. And then, yeah, so there's this position that's get passed in, and then this is the function that it calls, which basically just says, hey, OpenGL, my final position that I want you to put the vertex at is the position I passed in with a 1 on the end. You need to convert it to a vec4 because that's what OpenGL expects. Don't worry about that too much. Basically, it's just, we're not doing any processing at all. We're just passing the position straight through. Most OpenGL programs would do some sort of transformation in here to change this position, especially if you're talking about like 3D or something. So that's what it does first. And then once it's figured out the final positions of the 3 vertices in the triangle, then it says, okay, which pixels, or in OpenGL terms, they say fragment because technically it's not a pixel yet. So, but we'll just say pixels for simplicity. Which pixels is this triangle going to cover? And then for every pixel, it runs this code on the GPU, which determines what color to make the pixel. And these 2 shaders that I've written now, I feel like are probably the simplest shaders you could possibly write, because there's no processing at all. You could pass information from this one to this one and, you know, do lighting calculations and all sorts to figure out exactly what color you want it to be. But here I'm just saying the color that we're outputting is another vec4, so it's an array of 4 floats, and they're all 1s, which means white. It is the color white. Very simple. So now that we have these 2 shaders, we need to create a program from them. Like, we link them together to make a program. So we have the link shaders that we're going to copy. Yeah. Link shaders. Let's change it to our syntax. Just going to pass in two parameters. Vertex shader name and fragment shader name. And then so we create a program, and instead of looping through a list of shaders like in my other program, I'm just going to say attach the vertex shader name and the fragment shader name. And then we link them together. And what we end up with is a program. And that program is what we then say. Then later on, we're going to say, okay, OpenGL, here are my vertices. Here's the program I want to use. Now draw my triangle. That's basically what we're going to try and get to. Okay, so some of this is going to be very similar to what we had here. Like this becomes this, but it's actually failed to link shaders. Here we need these same types. That's null pointer. That's pointer to info log. That's our size. Pointer to link status. We need to define this. So I think again we're going to need to go in here, find out what it is, convert it to decimal. There we go. Cool. Okay. Fingers crossed. That should work. Okay, so we need to call link shaders now. So we do that with these two. And if all of our alignment stuff is working properly, then this should be working. If we start getting some weird errors, it could well be. So this should be link status. And this should be link status. It could well be that we've screwed up our alignment code. Still no issues so far. I don't know about how good my confidence is though, because the thing with graphics programming is you get the tyranny of the black screen. You know, your graphics programming is not working, and it's giving you a black screen. But then, how do you figure out why? Why am I only getting a black screen? Okay, let's have a look at some rendering code. So we need to make a buffer. We're going to simplify this a bit, because here I use a struct. I create a struct, but we don't have structs in our language, so okay, then we can just do this. So let's just try and convert all of this to something that works. Buffer name, pointer to buffer name. Buffer name, I guess, is an I32. GL array buffer. And buffer size is I64, it looks like. And the buffer size is going to be 9 times 4, or let's say 3 times 3 times 4. We have 3 vertices in the triangle. Each vertice has 3 floats, x, y, and z, and each float is 4 bytes. So this is the size of the buffer in bytes. Let's put that in there. Buffer name goes there. Yeah, we'll just call that buffer data. That's fine. So I think we're getting close. This is null pointer. So this part here, we can't do bitwise ORs. So we kind of need to take this and figure out what it evaluates to. And I might just run this program and print out what access hints is. Like that. There we go. So it's 194. So then we can come back here and we can just say, I think it's an I32 buffer access hints is 194. Boom. Okay, so that should create a buffer for us with enough space. And I've made it so that this returns a pointer to an array of floats. So we should just be able to index into that array and set our float values. Because what's happening here is we're creating a buffer on the GPU. We're saying it's an array buffer, which means it's holding our vertex data. And then these two lines here basically make it so that we can just access it like a regular pointer from the CPU, which just makes it easier to deal with. Let's just make sure we don't have any errors. Buffer data, we need to do that. Unsupported data type. Register named, okay. Interesting. And what is the data type? It's an F32 array pointer. Ah. So I've said here that floats, we can't do named registers for floats, but if it's a pointer to a float, then it's a pointer. It doesn't matter what it's pointing to. Pointers use general purpose registers. So if it's a float and it's not a reference, not a pointer, do we have to check whether it's an array or not? I don't think so. So this also, we need to make sure that it's not a reference before we start using these registers. Is there anywhere else that we do this where it's negation? Well, we should never negate a pointer. Right? If we're negating a pointer, something's gone wrong. And also, if we're doing a binary operation, we should not be dealing with a pointer. Type checking should take care of that. So I think that's... Oh, okay. Now we're getting some assembly errors. 225. Wow, we happen to be exactly on the right line. Move SD racks into RSP. So that should not be move SD. Okay. So there was one other place. It's in our copy. Yeah, see, we're using this because it's a float data type. But again, it's like if it's not a reference. If it is a reference, we just use the regular move. Okay. Okay. Okay, nice. So found some issues and fixed them up. So now, fingers crossed, we have a program to render with. We have somewhere to put our data. So let's put some data in it. So let's say 1, 2, 3, 4, 5, 6, 7, 8. So these three first floats should be the X, Y, and Z of the first vertex. So let's put it up on the y-axis. And the coordinate system that OpenGL uses is from -1 to +1 on the x and y axis. So -1 is the bottom left corner, and +1 is the top right corner, I believe. So if we say this is at, no, on the y-axis 0.5, but on the x and z it is 0, then it should be high up in the middle. Now we make a low one on the left, and then a low one on the right. Those are our 3 vertices. The order you do the vertices in does matter on OpenGL, but we're not culling the back face, which means it doesn't matter which way around you make the triangle, it's always just going to render it. Which probably doesn't, you probably didn't need to know that. Okay, so the last step, I think, is that we've already bound this, so we've already said use this buffer, but we haven't yet said use this program. I think that's the next thing we need to do. Yeah, here's use the program, and then these 2 lines are saying basically we have one thing that we're putting into the shaders, and that one thing is 3 floats. That's our position. It's kind of a long-winded way of saying that. And then use program. Maybe we can put this, let's put it here. In the other program that you just saw, I had it inside the loop. This in the render update, but it doesn't really need to be in this case because we're only using one program. It never changes. So let's just put it here. That needs to be GL float, and I think we can just pass false in here. And I think we can just use GL use program. I think over here I had a procedure because it does a whole bunch of validation. This is all validation before calling use program, but let's not worry about that. So let's just say program name. Okay, so that should be that. Incompatible types. Number and pointer to an I8. Line 83, column 5. That's this guy here. Okay. Does that need to be a null pointer? Yeah, the last parameter is a null pointer. Okay. So should I just go null pointer? Okay. Everything's looking good still. Okay. We're getting close. We're getting close. We're nearly at a minute 15 now, but fingers crossed that something actually renders when we get to the end of doing all this. So the last thing we need to do is we want to do a clear. I mean, this is not so necessary in this case. I mean, we don't really need to be re-rendering every frame because we're just re-rendering exactly the same thing. But we're just going to do a clear and then a draw. But this is a very complex draw, and we're just going to do draw arrays. What were the parameters for draw arrays? I did have it before. So it's the mode, first, and count. So I think the mode is going to be GL triangles. First is, we're starting at the first vertex and we're drawing 3 vertices. Okay. So I think we've done all the code and we did not get a triangle, which really sucks because I don't know what's wrong. I'm kind of gutted that we're not getting any output from anything. So I think these, hopefully that's working. But another thing in OpenGL is, and I did add the procedures here. There's this get error and this utility for error string. And what we can do, I don't think I did it in here, but I have another project. Here it is. You can do something like this. And what you need to do is, after every procedure, every time you call OpenGL, it might set some error state. So you can use this procedure I made to check that error state and print it out. And then we just need to call it after every OpenGL call. GL no error. I shouldn't have closed that other project so fast. Where is it? Astrum. Can I open this? Is it still indexing or something? There we go. Ah, it's 0. Okay. So make that 0. So GL error string is what we want to print out. What did I make that return? Oh yeah, an array of a million. I pointed to an array of 1,000,000 bytes. So that'll be our print B. And yeah, then we need the length. So let's just call it 100. I don't think the error message is going to be that long. Oh, so we need to put that outside like that. And then the idea is every time we call OpenGL, so we'll do it in these procedures too, we call check OpenGL error afterwards. And then we might see that we get an error somewhere. I won't do it in there. These two. Those. I think that's it. So do we get an error? Invalid token. 131. I've got a semicolon. Undefined reference to GLU because we need to be even more hacky and add GLU here. Okay, see, we've got this error message now. I'm pretty sure it'll just be, because I just guessed 100 characters, so just printed out 100 characters, but I think it'll be this first one, invalid value. So let's just, if we just like cut out a bunch of code and see whether we still get it, because we don't know where it's happening. Okay, that was fine, no error. So let's introduce that code. Still no error. Let's introduce this guy. Still no error. Introduce those two lines. Invalid value. So which one of those two lines is it? That one seems fine. This one has an invalid value. Let's look at the assembly for this. This is that byte alignment and then deallocation of the byte alignment. So these are all the parameters. We've got 0, 3. We're putting a variable into the third one. Yeah, GL float. Then we have 0, 0. Yeah, false is 0, 0 is 0. Okay, this is a problem. So you might remember if you watched the other calling C video that the parameters to a C procedure go in these registers, this one, this one, this one, this one, then R8D, then R9. But the problem is we've set the R8D parameter and now we do an expression. This is an expression, and as part of that expression, we write to R8, which overwrites this. These are the same register. R8D is a shorter version of this register, but like it occupies the same space. So this is overriding that, and that's a problem. I think what we need to do, what we can do is for our registers, it's kind of sucks because it's like the C calling convention is dictating what we can do. But because we have here that it's using, this will become register 8 and 9, what we can do is just say that for numbered registers, we actually start from 10. So whenever we do our expressions and stuff, it'll start from R10. And then up here, where we actually need R8 and R9 for these two, we adjust by going negative. So that should be 8 and 9. Okay, so the error is gone. Let's have a look. See, now we put it in R8, and now we're using R10 in our expression, and then putting the result in R9. So we got rid of the error, but we didn't get, because we took away the rendering code. Boom! Triangle. Yeah. So satisfying. So satisfying. Just to draw a triangle. It's a lot of code, right? To draw a triangle. 150 lines to draw a triangle. I mean, a lot of it at the top is just all these definitions. But hopefully that made sense. This clears the screen and then this draws the triangle. Which is pointless to do every frame in this case. But if we were to rotate the triangle, then we would need to clear the string so that the old triangles we rendered go away, and then redraw the rotated triangles. That's why you normally do clear and draw in a loop. So then you'd have like rotate, the rotate triangle code here maybe. So you'd rotate the triangle by modifying these vertices, and then you would clear and draw it again. And then you'd get a rotating triangle. Wow. Really awesome. I think it's really cool that we've got enough features in the language that we were actually able to pull this off. Some of it is definitely a bit hacky. I will admit this. there is some hackiness. There is some hackiness going on, but we were able to do it. Cool. It's a bit of a long video. We're at an hour 25 now. What I want to say to wrap up, I think we're at a point now where we have something interesting enough I think now what I want to do is render like a whole bunch of triangles and then do some sort of processing on those triangles per frame, like a rotation. Because then that becomes something that we would want to parallelize. And then we can play with what we actually wanted the language to do. Parallel processing, which we can move between the CPU and GPU. And then we can see the difference. Like if we run it single threaded on the CPU, how does it do? If we throw it across a whole bunch of threads on the CPU, how does it do then? We could even get into SIMD, to speed it up. And then if we throw it onto the GPU, how does that do? Yeah, it's a bit ironic that we are, like, this is the kind of thing that I actually want to avoid in my language. Having to write this code in a separate language and then compile it. Anyway, okay. I am pretty happy with that. We have a white triangle. So cool. Yeah, so thanks for stopping by. Looking forward to finally getting into this parallel stuff. Have a good one. Ciao for now.